In this chapter, we will be learning about logarithms. In this lesson, we will be looking at the graphs of exponential and logarithmic functions and transforming them. And we will start with exponential functions.
So an exponential function is written in the form y equals ab to the x. Here, let's zoom in on that there. It's written as ab to the x. So notice that the independent variable is up in the exponent, and that's why we call it an exponential function. Okay, our names are always based on where the variable turns out. Now, we're going to throw some restrictions on here. We're going to let b be greater than 0, and that's because that's because we're going to let x be an element of the reals. Okay, so our domain here is going to be all real numbers, and you'll see that in just a second here. But the reason why that's an issue here, why these have to go together, is because if we let x be an element of the reals, that means it can be any real number. For example, it could be a half or a quarter or a sixth or whatever. And if b, the base of the exponential here, is a negative, then this creates imaginary numbers when we plug those things in. And we just, at this point, we're not prepared to work with that. We just want to look at the exponential function on its own without adding that level of difficulty. Additionally, we're not going to let b equal to 1. Now, here, you could let b equal to 1. It'd be an exceptionally boring function because it would just be constant at whatever a is. Because remember, a here is not part of the base of the function. A is a stretch, if you will, a vertical stretch of this function. It is not part of the power here. So if we let b equal to 1, it'd be really, really boring. Now, additionally, when we find the inverse of the function, this won't make any sense at all. And so we're going to exclude that. Now, let's take a quick look at what these functions look like. Okay, so right here, this is the sort of graph that you get if b is greater than 1. So for example, if we let b equal 2, our graph would look like this. Okay, it kind of swoops up. As you go to the left, it approaches the x-axis. As you go to the right, it quickly rises. This is why we use that term exponential growth. When someone talks about something growing really fast, okay, we say it grows exponentially. That's because this is what that function does. It grows really, really quite quickly. This is what it looks like specifically if you let the base be equal to 2. Okay, doubling is actually an incredibly fast way to grow here. Now our domain, as I said before, is going to be an element of the reals. Our range, okay, well, it goes up, okay, it goes up to infinity, but when it comes down here, it's going to go through the point 0,1. Notice in both cases it goes to the point 0,1, which makes total sense because if you let x go to 0, no matter what the base is, it's going to be, well, except 0, but for all other cases there, when you put 0 in the exponent, it'll go to 1. But it never actually gets to 0. There is no exponent you can put on 2. Y equals 2 to the x. There's no exponent you can put there, no value you can put there that'll make this whole thing equal to 0. So my range here is going to be greater than 0. Not or equal to, just greater than 0. There is no x-intercept. Turns out it only approaches the x-axis. It never actually gets there. It does, however, have a y-intercept at 1. And now we're looking at this horizontal asymptote, okay? It does approach the x-axis here. It never gets to it, but it does get closer and closer and closer. So this is going to be the line y equals 0. Now, compare that to these two down here. And what we're looking at here is the sort of function that you get when b is a value between 0 and 1, okay? Now, we would call this a growth function. And often we'll call this one a decay function. Notice that really what we're looking at here, now it's not exceptionally clear from these two graphs here, but what this is really is just a reflection over the y-axis. And you'll see that come out in the lesson here. But yeah, we're just going to reflect this over, so instead of going up, now this thing drops down from infinity here, okay? And so this is what y to the 1/2 looks like. Starts high, drops down, and then again gets closer and closer to the x-axis. Our domain in this particular situation is still all reals. Our range, well, it's basically got the same look to it. It's just going the opposite direction. That horizontal reflections isn't going to affect the range here, so it's still greater than 0. There's been no vertical motion here, so there's no x-intercept still. The y-intercept under a horizontal reflection is going to be invariant, so the y-intercept is still 1. And that's still not going to affect the horizontal asymptote. So what's neat about this is that these qualities here of these graphs here don't change when you change the base from a value greater than 1 to a value between 0 and 1. It's just kind of neat. Anyway, you really need to be familiar with these shapes here. You probably should spend some time going over and trying to memorize these properties, although the truth be told here, after a while you should just know them even by just going through this work.
State which of the following are exponential.
Okay, so we're going to quickly run through this question right here, which just simply says state which of the following are exponential, like I said. It's important to be able to recognize when you're looking at an exponential function and when you aren't. Particularly because what will happen later on here is we're going to ask you to start solving equations, and every once in a while we're going to throw in an equation that isn't exponential, in which case the rules are much different for solving. So for example, take a look at this one right here. This one is not exponential because the variable is in the base of the power. Okay, if this had been 5 to the x, that would have worked here. This one right here, y equals 0.4 to the x, the independent variable, is in the exponent. It doesn't really matter what my base is, okay, as long as it's between 0 and 1 or greater than 1. So yep, there we go. Y equals 6 to the x, yeah, my variable is up in the exponent, base is 6, that's good, yep, that's exponential. Y equals x to the 1/3, yeah, nope, because again the variable is in the base and I don't want that. Okay, if to be exponential I want the variable in the exponent. Okay, come down here, y equals -2 to the x. Oh, that's tantalizing, but no it's not. And that's because the the base here is negative. The base here should be positive. Now if you're forgetting that restriction, we're right back up here where we said here that b has to be greater than 0. In this particular case here, as soon as you let b go to -2, this becomes what we would call a complex function. Okay, now all of a sudden the overriding point is that we're eventually taking the square root of negative numbers here. So nope, no good. Okay, now this one's a little bit more complicated. The division by 2 here outside, so here's my function, because there's the x is here. So this division by 2 is just going to be a vertical stretch by a factor of 1/2. So that's not really determining what the function is. So just take a look at this. Yeah, x is in the exponent. Now granted, we're doing something to the x here, but x is in the exponent. That's what needs to happen. And the base is an acceptable base. Yes, that's exponential. No, this isn't. This could be rewritten as 1/5 x to the -1. Now notice when I did that, I did not bring the 5 with it. Okay, I could have, but if I did, I'd have to put brackets around it. Okay, I could have written it like 5x to the -1, but I certainly couldn't have written it as 5 times x to the -1 just without the parentheses here. Again, notice that the variable is in the base here, so no, this is no good. Again, variable in base. Variable needs to be in the exponent. So there you go. Hopefully at this point now you've got a sense of what needs to happen to be an exponential, and hopefully that little bit of knowledge there will help you make good decisions when you're trying to determine how to solve an equation.
Write the equation of each exponential function graphed below.
Okay, well, we know that if this is an exponential function here, the equation is going to be in the form a b to the x. Now, a, again, is a vertical stretch. It is not part of that power there. Now, let's just take a quick look at the points that I'm giving here. Most specifically at this point, I want to take a look at this one right here. What happens when x is equal to 0? So when you let x equal to 0 here, we're getting y is equal to 0. So 1 is equal to a b to the 0. B to the 0 is going to be 1. So in this particular context, a is 1. Okay, so, and that actually makes a lot of sense here. If we're going through the point 0, 1, that suggests immediately that the a value is 1. Because a is a vertical stretch, it turns out whatever your your y-intercept is, that will be the same value as the a, just for exactly this reason here. You would plug in 0 in for b, it would eliminate that factor, and you're simply left with a equal to the y-intercept. So now we're just going to plug in a different point here, and it doesn't really matter. I've got 2 points to choose from, but let's be lazy. Let's choose this one. So if I choose to plug in -1 in for x, the value is 4. Well, that means b to the negative 1 is 1 over b. And if I reciprocate both sides here, I get that b is equal to 1/4. So therefore, I can write that this equation must be 1/4, y equals 1/4 to the x. And that's perfectly consistent with what I was expecting, because I know that when a function looks like this, it's a decay function, that the base should be between 0 and 1. All right, now let's take a quick look at this one here. We're going to come up with the equation of this function again. Notice that in this case that we're going through the point 0, 1. Okay, and as with the previous question, that immediately tells me that a is equal to 1. If I plug that point in to the equation of the function y equals ab to the x, the b to the x term will disappear, and I'll be left with a equal to 1 here. So good, there we go. So now I know that this has got to be y equals b to the x. Now again, I've got 2 points to choose from. Let's just choose the first one. So 5 is equal to b to the 1. Well, I love that, because I know b to the 1 is just b, so I know that b is equal to 5. So I can come down here and write that the equation of this function must be y equals 5 to the x. Awesome. Okay, now this one's a little trickier. Notice that I can't tell exactly what the y-intercept is. Now, based on the scale, I'm assuming it's 1. Okay, and I'm almost positive it's 1, but I don't know for sure. So I really am stuck just using the information that they've given me here. So now I've got 3 points here, but in my equation, y equals ab, oops, sorry, I forgot the a. I said it, I forgot it. ab to the x here, I've got 2 variables that I need to find here. I only really need 2 points to do this. So what I'm going to do is I'm going to plug in this 3, 8. Okay, so 8 is going to be equal to ab cubed. I'm also going to plug in the point 2, 4. There's 2 variables I'm looking for. I need 2 points on the graph to figure this out here. So 4 is going to equal ab squared. Now, in the past, when you have done work with systems of equations, you added or subtracted or did substitution. And substitution will work wonderful here. Addition, subtraction, not so much, because I've only got 1 term on both sides here. However, I can also use multiplication and division to get rid of a variable here. And so what I'll do here is I'll use division. Okay, not quite so clear here. I hope that's visible. I'm going to use the division symbol there. So 8 on the left-hand side here, 8 divided by 4 will be 2. And when you divide the term on the right-hand side with the term on the right-hand side here, the a's will cancel, and I'll get b cubed divided by b squared is simply going to be b to the 1. Okay? Remember, you just subtract exponents when you divide powers there, which is awesome. I already know what b is. So now this tells me that I've got, at this point here, y equals a times 2 to the x. Now let's just pick a point here, like for example that point 2, 4. So 4 is going to equal a times 2 squared. Okay, well 2 squared is 4, so a is in fact equal to 1. It looked like it was 1, but I didn't want to just read that off the graph in case it was something goofy like 0.9. Okay, in which case I was wrong, close but wrong. So now I can say that my equation is therefore y is equal to 2 to the x. There we go.
Now we'll take a couple of moments to talk about the transformations of exponential functions.
Okay, so just for a couple of seconds here, I just want to draw your attention to something here that you might even at this point just instinctively do correctly, but we're going to just make it kind of an explicit statement here. We're going to look at the transformations of exponential functions here, and I'm just going to zoom in here. When you plug stuff in, okay, to the exponential function, this is your base right here. Okay, c is taking the place of the base here. A, B, H, and K. These are the regular values that we've been using up to this point for transformations here. And they all perform the exact same role here. Now there's a chart underneath here that you can look at, but I'm just going to run through and summarize it really quickly. A is going to be a vertical stretch. Now additionally, because it's the vertical stretch, okay, if there's no translation like this, if there's no vertical translation, it's often, okay, the y-intercept. Now, actually, I should say I should probably delete that because you know what? The vertical translation and the horizontal translation will both change that. In a lot of cases, though, we're not translating it left or right or up and down, and so A does become the y-intercept here. But, sorry, second thought, I'm probably better off just not mentioning that. B is going to be your horizontal stretch, the same as before. H is going to be your horizontal translation, left and right. And K will be your vertical translation. Now, this one we can make this comment. None of the transformations associated up to this point, if you ignore this one, none of these transformations here are going to change the horizontal asymptote that you get with an exponential function. The only one that will is going to be that vertical translation. And so as a result, because that asymptote should be at the value y equals 0, when we translate that vertically up and down, the result is that we get that horizontal asymptote. So y equals k is that horizontal asymptote. Okay, and all this is saying right here is where k is a constant, it's the base. Okay, this is the base of the exponential. And that's all that this chart, by the way, is saying as well, just kind of summarizing up all that information.
Describe the transformations for each compared to the graph of y equals 3 to the x. Y equals 2 times 3 to the x minus 4.
Okay, so there's a few things we're being asked to do here. First of all, we're going to identify the transformations. Now, let's just take a quick look at this. Notice that the 3 here is the base of the exponential function. Okay, so the 3 is not the issue here. Okay, this does not reflect a transformation that's been applied to the function. That is part of the function. So what has been applied, though, is there's a 2 out front, which means there's been a vertical stretch by a factor of 2. Okay, and then up in the exponent here, I'm subtracting 4 from the x here. Now think about what you would have to do to isolate the x. I would have to add 4. So it's going to be a horizontal translation 4 right. Okay, now that becomes our mapping notation. Okay, 4 to the right is x, whoops, sorry, I put a comma there quicker than I wanted to. X plus 4. And then a vertical stretch by a factor of 2 means I'm multiplying the y-coordinate by 2. Now let's just think about this. How is this going to affect the horizontal asymptote? The horizontal asymptote for y equals 3 to the x, the horizontal asymptote should be y equals 0, right? Now a horizontal translation, if you got a horizontal line and you move it left and right, it's not really going to change that line. But neither will a stretch by a factor of 2, a vertical stretch, because the invariant points for that will be on the x-axis, and that's where my asymptote is. So the long and short of it is my horizontal asymptote is going to stay at y equals 0.
Y equals negative 1/2 times 3 to the 1/5 x minus 5.
All right, with this question we've got a little bit more going on here. And by a little bit, I mean a bunch more going on. Okay, first of all, again, we're going to reiterate this, that the 3 is not a transformation. The 3 is the base of the function. Okay, the base of the exponential function here. That is part of the definition of that function here. But everything else here, it does correspond to a transformation. So first of all, we see a negative in front. That takes the place of a vertical reflection here. Okay, so a vertical reflection. This is going to be over the x-axis. Okay, good. The 1/2 here is going to end up representing a vertical stretch by a factor of 1/2, because I'm multiplying it by the function here. Now I'm going to move up into the exponent here. Notice that I'm multiplying x by a fifth here. Well, what would I have to do to get x by itself? Well, I have to multiply by 5 when I get that down here. Now, at this point, you might not know how you would even do that, and we will discuss that in the remaining parts of this chapter here. But for right now, I would have to multiply by 5. So that's going to be a horizontal stretch by a factor of 5. And then this negative 5 being subtracted, sorry, the negative 5 being added to the back here is going to represent a vertical translation 5 down. This all translates over very, very directly into my mapping notation. So I had a horizontal stretch by a factor of 5, means I'm going to multiply x by 5. Now everything else was vertical. So first of all, there was a negative 1/2 y, and then we subtracted 5. How do these affect the horizontal asymptote? Well, A horizontal stretch won't change a horizontal asymptote. Neither will a vertical reflection or a vertical stretch. The only thing that'll change it is this 5 down. It's supposed to be, okay, y equals 3 to the x. It's supposed to be y equals 0, but it's been moved 5 down, so my new asymptote is going to be y equals -5. That's our horizontal asymptote.
Describe the transformations for each of the following compared to y equals 1/4 to the x. Y equals 1/4 to the -2 times x plus 1 minus 8.
Okay, so this question is similar to the one that we just, or the two that we just did. It's just that this time we're looking at this particular function, y equals 1/4 to the x, as opposed to 3 to the x. So let's identify the transformations. Again, that 1/4, because this is a new question, that 1/4 is actually the base of the exponential function. That hasn't changed. So there's no, how do I say this? There's no transformations that I associate with that. So now I look at what's going on with this function here. Look at my exponent here. I've got a -2, then in parentheses x plus 5. That negative corresponds to a horizontal reflection over the y-axis. Okay. The 2 here, if I was to try to isolate the x here, and again, at this point you might not know how that's even going to work, but you will. If I try to isolate the x there, I would have to divide by 2. That corresponds to a horizontal stretch by a factor of 1/2. And then I've got this x plus 5 up there. Well, that's going to correspond to a horizontal translation 5 to the left, because I'd have to subtract 5 to get that by itself here. And then out here, I've got this -3. It's happening outside the function, so it's a vertical translation 3 down. All right, this becomes directly, or moves directly into our mapping notation. So reflect horizontal, sorry, no, that's what I meant here. Horizontal reflection over the y-axis. Horizontal stretch by a factor of 1/2, again, means I'm multiplying x by 1/2. And then 5 to the left means subtract 5. Vertical translation 3 down means I'm subtracting 3 from the y coordinates. Now remember, when I list the transformations, I'm really describing what that image point is doing. Now, just like in the previous couple of questions here, when we ask about the horizontal asymptote, the answer really has to do with the vertical translation, because a horizontal reflection won't change it. If you take that horizontal line, flip it horizontally, it doesn't do anything. Stretch this thing horizontally, it's still not going to do anything because it's an infinite line. And moving an infinite line 5 to the left, again, won't change anything if it's horizontal, but this one will. So y equals 1/4 to the x here should have a horizontal asymptote at y equals 0. I've moved it 3 down. So my new asymptote is going to be y equals -3, 3 down from 0.
And now we'll introduce the logarithmic function.
Okay, so now we're going to take a look at a logarithmic function. We're going to introduce this concept, and you'll see what context this works in. So a logarithmic function is the inverse, there it is, of the exponential function, okay, the inverse. That's the big idea. So we'll start off with, let's just take a quick look at y equals 2 to the x, okay? So y equals 2 to the x, make that a little darker there. So the first step in coming up with the inverse is to interchange the x and the y here. So again, what you're seeing here should be x equals 2 to the y when we interchange the x and the y. Now the thing is, up to this point here, once you've got it like that, let's just zoom in. Okay, once you've got it like this, x equals 2 to the y, how do you solve for y? What algebraic tool do we have for bringing that y down so we could get y equals? And the answer is, really, we don't. And so what had to happen here is we had to kind of invent a notation for this. And the notation that we've got is what we call logarithmic notation. So to do this, we solve for y. We say when it can be written like this, then y equals the log, and a logarithm has a base. Okay, just like an exponential function has a base, a logarithm has a base, but we write it in the form of a subscript right here. So log subscript 2. Okay, really important that you don't think of this as a big 2 up here. It's a little 2 that's been kind of downplayed here. And we throw the x here. These two are considered to be identical to each other. They're saying the exact same thing. So This is just a way of getting y in this expression by itself. So x equals 2 to the y, which is the inverse of the exponential, is the exact same thing as y equals log base 2 of x. Now, notice right now, we just started looking at logarithms. I want to point this out right away. Notice that the log base 2 of x is equal to y, and in this form, the y was the exponent on the 2 there in that power. I want you to know something here. Logarithms are exponents. Okay? A logarithm is an exponent. And as such, when we start to look at the laws that govern logarithms, you're going to see that they are, in fact, the laws that govern exponents. They're the exact same thing here. So again, that's the relationship between the two of them in our little box here. Okay, you're going to see our different forms here. So the log base a of x is equal to y means the exact same thing as x equals a to the y here. So just notice the comparison between them. The base of the logarithm is the same as the base of the exponential function here, okay? When I'm just converting between forms here. A logarithm is an exponent, so in the exponential form, whatever the logarithm is equal to, that is the exponent on that base. And then the argument of the logarithm becomes the other side of that exponential function there, okay? So log base a of x equals y means the exact same thing as x equals a to the y. These are identical. Okay. Now, but remember, this is the inverse, okay, of y equals a to the x. I got to keep that in mind here, that x equals a to the y is the inverse of y equals a to the x. These two are the same. So because this is the inverse of this function right here, the log base a of x equals y is also the inverse of this function over here. There's just a few things here that you got to make sure that you keep straight in your head as we go through some of this work here. Now let's go take a look at this. Let's take a look at the graph looks like here. Here's our exponential function, y equals 2 to the x. Okay, good. And we've talked about these before here, so I'm going to quickly run through these characteristics here. Sorry, I can't believe I just did that. Ugh. The domain, and we've seen this before, is x is an element of the reals. There's no restriction on the value of x here. Okay, you can go infinitely to the left and the right. There's no gaps in it. There you go. Our range is going to be greater than 0. Okay, this graph here, as you go further and further to the left, is going to approach the x-axis, but it'll never touch it. As such, there are no x-intercepts. Our y-intercept, if you make x equal to 0, our y-intercept is going to be 1. And as we've said before, the x-axis here, this horizontal line, that's our asymptote, and that occurs where y is equal to 0. Now, let's figure out what the log function does. Well, the log function is the inverse of this, which means it's the reflection over this line here, y equals x. So the point 0, 1 is going to become the point 1, 0. Okay. The point 1, 2 is going to become the point 2, 1. Okay, so I probably should write those down. You got 1, 0. This is going to be 2, 1. The point 2, 4 is going to become the point 4, 2. And the point 3, 8 is going to become the point 8, 3. Okay. It's got an asymptote here where y is equal to 0, which means the asymptote for the inverse should be now x equals 0, and that corresponds to the y-axis. So this thing's actually going to look like this. It's going to slide along the y-axis. It's going to go through that point 1, 0, and then it's going to connect the dots that I just drew right here. So this right here is going to be y equals the log, in this case here, base 2 of x. Now let's zoom out a little, out a little bit here. I want to fill in the properties of the logarithmic graph here. Well, my domain for my logarithmic function is going to be the range of the original function, because remember, these are inverses of each other. So these are actually going to swap here. My domain is going to be x is greater than 0, and my range will be all reals. Same thing for my x and my y intercepts here. My x-intercept is going to be 1. Okay, it goes through the x-axis at 1. But my y-intercept, well, notice the logarithmic function is never going to touch it. There is no y-intercept. And we've already talked about this. The asymptote here was initially y equals 0, but again, we're flipping x and y, so this becomes x equals 0. We got this vertical line. Okay, so those right there are the characteristics of the logarithmic graph. Now, let's take a quick look. We'll zoom in on this. Let's take a look at some of the characteristics of the log function. First of all, the x-intercept is 1. We got that. There is no y-intercept. Okay, you want to remember that. Unless you've transformed it, there's no y-intercept here. And it's got a vertical asymptote at x equals 0. We've just discussed that. Its domain is is going to be values of x greater than 0. Now, not or equal to. Okay, please remember that. It's a simple mistake to make, but it's not or equal to. And its range is going to be all reals. Now, there's also an interesting, another kind of side little relationship here. I had mentioned before that when you've got an exponential function going up here, it goes up incredibly quickly. And so sometimes you'll hear people use that word, you know, something was growing exponentially to describe how fast it goes. Well, when you invert that, you get the logarithmic function. The logarithmic function also grows forever, but it does it very, very slowly. Whereas the exponential function grows really fast, this one grows really slowly. It does, however, have an infinite range. Okay? And once again, log base a of x is equal to y is equivalent to x equals a to the y. These two are exactly the same. Now, here's my logarithmic function. Notice where my little variables show up here, and you're probably wondering, or you're not wondering, but you probably recognize where I'm going to go with this. Okay, we're going to talk about transformations, because you can transform a logarithmic function just like you can any other function. A here is going to be responsible for the vertical reflection and stretch. B will be responsible for the horizontal reflection and stretch. H is a horizontal translation. K is going to be my vertical translation. Now in this case right here, the one thing to remember is that the logarithmic function has a vertical asymptote. And so if you take a vertical line and translate it left and right, that translation becomes the location of the vertical asymptote. And so as a result here, whenever we can get that x equals h, okay, basically whatever value of x here makes this thing equal to 0, that's going to be my vertical asymptote. It's just an easy way to find it.
Determine the inverse of each of the following. Y equals 3 to the x.
Okay, well the first step we got to do here is switch the x and the y, so x is equal to 3 to the y. But I don't want to leave it like that. I want to be able to solve for y here, so this is an exponential form. I'm going to have to use the logarithmic form here, so y equals the logarithm. Now remember, that works because a logarithm is the exponent. The base of the exponential here was 3, so the base of my logarithm is 3. And then the argument of my logarithm is whatever that power was equal to. So that right there is the inverse of y equals 3 to the x.
Y equals log base 4 of x.
So this one right here, we're starting from a different place here, but you can probably guess where this is going to go. If I'm looking at a logarithmic function, my inverse is going to be the exponential. First thing I'm going to do though is swap the x and the y. Okay. Now, to switch forms here, because I want to get y equals, what I got to remember here is that the argument of the logarithm equals the exponential. And I said the exact opposite with the previous question, but that's because we're going in the opposite direction. The base of my logarithm is the base of my exponential function, and a logarithm is the exponent. So y equals 4 to the x is the inverse of y equals log base 4 of x.
X equals 20 to the y.
So the first thing I got to do here is swap the x and the y. Y is equal to 20 to the x. And that's actually where I'm going to stop. That's all I got to do here. Part of the issue here is recognizing when a logarithm is required and when it isn't. This right here, this is the inverse of this guy right here. This could be written in a logarithmic form here, okay? I would solve for y here by making y equal to a logarithm, because the logarithm is the exponent. That's the exponent here. Since the base of the exponential is 20, the base of my logarithm would be 20. Okay, and the argument of the logarithm is whatever the exponential function equals. So that's, there we go. So this is equivalent to y equals log base 20 of x. Its inverse, however, I would just swap the x and the y, and that becomes this guy right here. I've already isolated the y. I'm done. I'm happy.
Determine the transformations for each equation compared to y equals log base 3 of x. Y equals negative 2 times log base 3 of x minus 3 plus 6.
Okay, well, we did questions similar to this one with the exponential functions here. So the first one we're going to do is lift off the transformations. And we're just going to do this left to right. So I see a negative to start off with. That is a vertical reflection over the x-axis. Okay? The 2, it's outside the function. It's been moved over from the y, so this is going to be a vertical stretch by a factor of 2. Good. Now I move on. What I've got, I'm going to move inside the function here. There's no coefficient with the x here, so there's been no horizontal reflection or stretch there. So just a horizontal translation. And what do I got to do here to get x by itself? Well, I got to add 3. So this is going to be horizontal translation 3 to the right. And then out here is this plus 6. That's a vertical translation 6 up. All right, good. Now, let's go to the mapping first. We're being asked for a few things here. Let's take a look at the mapping. So first of all, I got x comma y. Now, remember, I can relate all of this. All of this description here is describing what this point is doing. So horizontally, 3 to the right means we're going to get x plus 3. And then vertical reflection over the x-axis is negative y. There's a stretch by a factor of 2, so we're multiplying that by y. And then 6 up means I'm adding 6 to that. So there's my image point. Now let's talk about this. The vertical asymptote. How is any of this going to affect the vertical asymptote? Well, a vertical reflection, flip that over, won't change a vertical asymptote. Stretching that by a factor of 2 won't change the vertical asymptote. Neither will moving it 6 up. But moving this 3 to the right will. So my vertical asymptote here is going to be x equals 3. Now my y-intercept is going to occur when x is equal to 0. Now let's just take a quick look at this. So for my y-intercept here, if I let x equals 0, that's going to be y equals negative 2 log of 0 minus 3 plus 6. Now, 0 minus 3, the log of 0 minus 3, that's going to be negative 3. Oh, sorry, this is the log base 3. I forgot that. We're not, at this point, going to allow you to take the log of a negative. So this means that we're not getting a y-intercept. There is no y-intercept. Now, does that make sense? Let's just think about this. A vertical reflection, okay, a logarithmic function should look like this. It should look like this. A reflection over the x-axis is going to make it look like this. Vertical stretch by a factor of 2 is going to make it look like this. 3 to the right is going to move it this way. So what's going to happen here is that vertical asymptote is going to move over, and then I'm going to move that whole thing 6 up. So I've moved it away from the y-axis here. Yeah, it makes perfect sense that this thing's not crossing over the y-axis here. My domain, in fact, is going to be x is greater than 3. So yeah, these two are basically telling me the same thing. In a slightly different way, but yeah, they're agreeing. My range is going to be, as it always is with that logarithm here, y is an element of the reals. So those are the things that we're looking for this function.
Y equals log base 3 of 1/3 x plus 9.
All right, so we're going to finish this one up here by looking at a problem that looks like this guy right here. I'm going to identify the transformations. So when I come across here, there's nothing multiplied out front here, so there's no vertical stretch or reflection. Inside here, I am getting, though, a horizontal stretch by a factor of, well, what would I got to do to get x by itself here? I have to multiply by 3, so it's going to be by a factor of 3. I've also got a horizontal translation, but be really careful. Don't let me screw you up with this one here. I need to factor that stretch out of the translation here. I need to rewrite this, and we've seen this before in the transformations chapter and even in the trig chapter that we did. What I got to do here is I got to divide out that horizontal stretch here. And so that's going to make this plus 27. Because remember, when I take 9 and divide it by 1/3, I got to multiply by the reciprocal. And if you distribute this 1/3 back through, you should notice that you go right back to this guy right here. Now that is a horizontal translation, 27. And remember, to get x by itself, I'd have to subtract. So 27 left. So yeah, so what I had here is I had a logarithmic function looks something like this. Stretch it horizontally is going to make it look like that, and I'm going to move that whole thing 27 to the left. This thing is going to be way over here looking like that. So my vertical asymptote. Well, a horizontal stretch won't change that, but that horizontal translation will. This is now going to be at x equals negative 27. 27 to the left. My y-intercept is going to occur when I plug 0 in, so y is going to equal, sorry, I should identify this as being the y-intercept, the work I'm about to do. I'm going to make x equal to 0, so y is equal to the log base 3 of 1/3 of 0 plus 9. Well, 1/3 of 0 is 0 plus 9 is just going to be 9. Okay, so y is equal to log base 3 of 9. Now, let's just think about this. A logarithm is an exponent. So let's take this down here. A logarithm is an exponent. So what is this saying? Well, it might help us to convert this to exponential form. The base is 3. The exponent is the other side of the equation here. So a logarithm is an exponent. So 3 to the y is equal to 9. This is now a very simple little exponential equation, and we solved these a little while ago. I need this to be common basis here, so 3 to the y is equal to 3 squared, that's 9. So y is equal to 2. That's my y-intercept. Y-intercept is 2. Good. My domain, based on just that little bit of work that I spent following where that function went, is going to be x is greater than negative 27. My range, just as it has been for a bunch of previous questions, is going to be all reals. And my mapping. Now normally I would have done my mapping first. There just wasn't a whole lot going on here with my mapping. It's pretty easy to follow here. X comma y is going to become 3x, minus 27, not plus 27, minus 27, comma y. There was no change vertically. So this is all that we're looking for this particular function.